sporting goods company has 3 stores in 3 different towns. They want to build a distribution center so that the distance from each store to the distribution center is as close as possible. Okay? So we want to find a point where they could put the distribution center so that they would be equidistant to all 3 stores. Yes? Okay? Between what and what? Between which stores? You want to do B and C first? Okay, so here is the segment here, and this right here, that's about the midpoint, right? Okay, so that would be the perpendicular bisector. Okay. Okay, yeah, we will make the triangle here in just a second. Okay, but, okay. Alright, so make a triangle with A, B, and C. And he said, I did a very good job finding this point on that. Okay, and so let's make a triangle here. Make this. That works. Okay, so you drew a line between store B and C, and if we draw a line that's the perpendicular bisector, okay, then any point along this line is equidistant to the 2 endpoints, right? Like we talked about yesterday. Yes? If we did the same thing with between A and B, look about the midpoint. Okay. And there is the perpendicular bisector. Kinda. And that's all. Okay. So there's another perpendicular bisector. So any point along this vertical line is going to be equidistant to store A and B, right? They cross right here. So it would be safe to say that this point is equidistant to B and C, right? It's equidistant to B and A, yes? So it would be equidistant to all 3. Even if I drew the other one, the same thing would happen. They're going to all intersect right there at that point. Because this is probably the perpendicular bisector right there for between A and C, okay? All right, so that's how you can figure out a point that is equidistant to all the vertices. Okay? When you have 3 lines that intersect at a single point, those lines are called concurrent lines. Okay? So all 3 of these lines right here are concurrent lines. The point where they intersect each other, that is called the point of concurrency. Okay, so 3 lines, they all intersect at one point, are called concurrent lines, and the point where they intersect is called the point of concurrency. Alright, so we saw that if we drew all 3 perpendicular bisectors of a triangle, okay, we have triangle ABC here, and this right here is a perpendicular bisector, this is a perpendicular bisector, and that is a perpendicular bisector, okay? They all intersect at this point, okay? And that point is equidistant to each one of those vertices. So all 3 of these distances are the same. Okay, that's kind of like the problem that we just did. Draw the perpendicular bisector, each one they intersect here. You know, when you have a line that lies in the perpendicular bisector, it's equidistant to the endpoint. This point right here is called the circumcenter. Okay? Okay, this point is called the circumcenter. Okay? It is created by the perpendicular bisectors, and it's equidistant to the vertices of the triangle. Okay? So let's write that down. We're going to say the circumcenter is created by the perpendicular bisectors of a triangle and is equidistant to the vertices. So you draw all three perpendicular bisectors. They intersect at a point called the circumcenter, and that point is equidistant to the vertices. Here is some examples of three different ones. Okay, this is an acute triangle. In an acute triangle, and you draw all three perpendicular bisectors. I didn't write it, okay, but each one of those is a perpendicular bisector. Then the point, the circumcenter is going to be inside the triangle, and each one of those distances are the same. Okay. Here's an obtuse triangle. Each one of these is a perpendicular bisector. This one's a perpendicular bisector this side. There's that one this way. In an obtuse triangle, they're going to intersect outside of the triangle. Okay, and it too, that point is equidistant to each one of the vertices. In a right triangle, again, these are the perpendicular bisectors. The point of the concurrency, the circumcenter, is on the triangle. Okay, and again, that point is equidistant from all the vertices. Okay, so the circumcenter is created by the perpendicular bisectors of the sides, and that point is equidistant to the vertices of the triangle. Okay, now, how can you construct a circle that contains the three vertices of the given triangle? Okay, when you have a triangle and you have a circle that goes around it, such that each one of the vertices touch the circle, this is called a circumscribed circle. Okay, it's called a circumscribed circle. And all points on the circle are equidistant from the center of the circle. What's that segment called? From the center to the circle, what's that called? Right, the radius. And all the radii in a circle are always equal. So, the vertices of the triangle must be equidistant from the center of the circle. So what happens is we go and we create the perpendicular bisector of each one of the sides of the triangle. Okay? So if I did the perpendicular bisector here, and I did the perpendicular bisector here and here. Okay? They intersect at this point called the what? The circumcenter. Okay? And this circumcenter right here, then, we know by what we just learned, is equidistant to the vertices. So if I had a triangle and I wanted to draw a circle around it so that each point touched it, I would find this point and then I would use my compass tool and measure the distance and go all the way around. And it would encompass all the sides and all the vertices of the triangle. Okay, it's called a circumscribed circle. So right here, the point of concurrency of the perpendicular bisectors of the triangle is the circumcenter. Okay, so that's basically what it's saying. Okay, so let's look at this. A city manager wants to place a new emergency siren so that it is the same distance from the school, hospital, and recreation center. Okay, so here is the school, here is the hospital, and here is the rec center. Okay, and I want to put a siren that is equidistant to each one of those points. Okay, so connect all these to create a triangle like we did before, right? Now, I'm not going to make you get out your compass and do this. It's messy. I've done it before. It's very messy. But you can kind of eyeball it. Kind of find the midpoint about right here, and then you draw a line perpendicular. Then you come over here, and you find about the midpoint, and you draw another line that's perpendicular. And here, another one, you're going to draw another line that's perpendicular. And you can kind of eyeball it to see the point at which you would want to put the siren so that it is equidistant from those three important places. Okay? engineer, you might, or an architect, you might ever use that concept. Sure, what if you're building a building, right? You're trying to decide where to put the bathroom. And let's say your building has 3 main office hubs on the floor, right? You probably want to put the bathroom about distance from all of them, yes? Or you would get people complaining that they have to walk, right? Okay, so definitely something that you might use. Okay, now we're going to talk about what happens with angle bisectors. Okay, the angle bisectors of angles of the triangle are concurrent at a point equidistant from the sides. Okay, so what happens here is, yesterday, remember, we drew the angle bisector, right? Okay, and we said that any point on the angle bisector is equidistant from the side of the angle, right? Okay, so if I draw all 3 of them, okay, this is an angle bisector, this is an angle bisector, and this is an angle bisector, okay? They are going to intersect at a point that is equidistant to the sides, okay? So, this, and it's always perpendicular. When you talk distance, it's perpendicular distance, okay? So, each one of these distances, each one of these perpendicular distances are the same, right? So, this tells me, oh, in this point where they intersect, right there, it is called the incenter. Okay? And your incenter is created by the angle bisectors and is equidistant yeah, it's right there on that. It's got the RAM on it and the charger should be right. Angle bisector is equidistant from the sides of the triangle. So you draw all 3 angle bisectors that should intersect at a point because they're concurrent lines. Okay, so all 3 angle bisectors intersect at a point. That point is called the incenter, and it is equidistant to the sides of the triangle. Okay. How can you construct a circle that intersects each side of a given triangle in exactly 1 point? Okay, so when we did perpendicular bisector, we wanted the circle to go around the triangle so that each point touched the triangle, right? That was called a circumscribed circle. And you create it from the circumcenter, yes? Okay, when you want this time, we want to create a circle inside the triangle, okay, that only touches the triangle at 1 point. That's called a tangent point. We'll learn more about that after Christmas, okay? But we want to create a circle inside the triangle that only touches it at 1 point, okay? So what do you think we're going to use? Okay, well, it is called the incenter, right, okay? What creates the incenter? The angle bisectors, right? So if I took each angle and I drew the angle bisector, okay? Here's an angle bisector, here's an angle bisector, and here's the angle bisector, right? Bisect all those angles. Okay. Alright. So they intersect at this point right here called the incenter. Remember, the incenter is equidistant to the sides of the triangle. So if we use this as the center of our circle, we would measure from here to where it touched the circle. Okay? And that line segment would represent the what of the circle? Center to the side would represent the radius. You would want to keep this distance constant all the way around, right? So if you kept it constant, it would intersect the triangle at this point, and then it would go, and then this point, and then this point. Okay? Where you drew the distance from the center. Okay? Alright. So that point, like I said, is called the incenter. And this kind of just tells you what to do. Here, just like I said, draw the angle bisector and intersect here. You really just have to draw 2 of them because you know that the third one's going to intersect. Okay? Then you figure out the radius, the distance from the center perpendicular to the side, and then using that radius to go around the circle. Okay? This circle is called an inscribed circle. Okay? Because it's inside the triangle. So the inscribed circle is inside the triangle and it's created by the incenter. The circumscribed circle is on the outside of the triangle and it's created by the circumcenter. See how they kind of go together? Okay, and it goes outside. So circumscribed circle is along the outside, created by the circumcenter. Inscribed circle is on the inside, created by the incenter. Okay, so let's work a couple of problems. Find each measure if J is the incenter of triangle ABC. So J is the incenter, which means it's created by the what? Angle bisector. So these two angles are equal. These two are and then these two are. Okay? Alright, so those are angle bisectors. They intersect at the incenter. And what relationship does this have to the triangle? Equal to what? Well, if you draw a segment from here to the side on each one of them, each one of those little segments are equal, yes? Okay, so they give us JE, which is 6x plus 2, and they give us JF, which is 2x plus 14, and we want to find JF. Do those two segments have a relationship? They're congruent, right? So we're going to set them equal to each other. 6x plus 2 equals 2x plus 14. So subtract 2x from both sides, subtract 2 from both sides, and we get x is 3. Is that my answer? No, we have to go back and plug it in. And so we end up with 2 times 3 plus 14, 6 plus 14, which is 20. Okay, so JF is 20. What else is 20? JE and JD, right? All of those are 20, right? Okay, now I'm going to add a question to it. I want us to find JB. Okay, we're going to find JB. Alright? Now, I'm going to tell you, I'm going to change something just a little bit. I'm going to tell you that this is 48 right here. BE is 48. Okay, so I'm going to add that to the cross. Alright, what am I going to do then to figure out JB? Okay, right here I have a right triangle created, right? And I know two parts of it, so I can do the Pythagorean theorem to find the third part. So I'm going to do 20 squared plus 48 squared equals c squared. So that is what? 400 plus 48 squared is a large number. 2,304 equals c squared. So that's 2,704 equals c squared. Okay. So my JB would be... Okay, here's another one. No questions on that? Okay. Measure of angle JAC. JAC, which is this guy right there. Okay, so we're going to look at the big picture of the triangle. So we're going to look at the big picture of the triangle, okay? How's that going to help me? Okay, JCA, so this right here is 32. That means this whole big angle here is 64, right? Okay. Right, because this is going to be 34 here, so it makes this 68, right? Add these two together, subtract from 180. And you get the big A, and then you have to divide by 2. Okay, good. So if I take 68 and 64, that's 132. So 180 minus 132 is 48. And so then I divide that by 2, and I get 24. So this right here is 48. So then this angle here is 24. Okay, everybody see how I did that? Alright, any questions on that? I think this next one's kind of like that. No, maybe it's the next one like that. And QP is 3 times the quantity x plus 1. So this right here is 3 times the quantity x plus 1. And RP, that is 5x minus 3. What is the radius of the inscribed circle of triangle JKL? I don't even know what that is. Okay, yeah, I am going to have to distribute there, which is 3x plus 3. You're right. Are they equal? Yes, because this point here, UP and RP, what is the radius of the inscribed circle? You would have, oh, and this is an angle bisector, so is that. So we can see that these are angle bisectors, and they intersect at the incenter, which is equidistant from the two sides. So we know these two have to be equal to each other. So we're going to set 3x plus 3 equal to 5x minus 3. And so that would be 2x equals 6. And so x is equal to 6. But is that my radius? No. My radius, I would have to go back and plug in 5 times 3 minus 3. So 15 minus 3, which is 12. Okay? So the radius of the inscribed circle, this right here, is going to be 12. And then you would, terrible picture, but that's what it would kind of look like. If I wasn't drawing it, it would pull out there. Alright. Last set of questions here. Some of these are similar to kind of what we did a while ago. If the measure of angle BAF is 15, so BAF is 15, and CBF is 52, what is ACF? ACF, so this is what I'm wanting right here. Okay? Now, you can see that these are both angle bisectors right here, AF and BF, right? So, and since CF intersects it, it's going to be an angle bisector also. Okay? So like that one we did a while ago, if this right here is 15 BAF, then what is EAF? The whole angle is 30, but EAF is 15, right? That will hit. Okay, what's this big angle here going to be? 104, right? Okay, and this one you can make 2x. Actually, going to subtract, some people 180. Or go ahead and just add these two together, which is what? 134. And subtract from 180. Is that 46? Is that right? Did I do my math right? Okay, so that means that this angle that I'm looking for is what? 23. Okay? Last one. EF is 3y minus 5. DF is 2y plus 4. What is the distance from F to AB? F to AB, which would be the perpendicular distance right here. Okay? So what'd you say? It's center. So all these distances here are equal, right? Okay, so I've got two of them. I have EF and I have DF, so I can just set them equal to each other, right? So 3y minus 5 equals 2y plus 4. So that's y equals 9. And what is the distance from AB? We have to go back and plug in, right? So if we found, let's say, EF, that would be 3 times 9 minus 5, which is what? 7 minus 5, which is 22. Alright. So just to recap, what is created by the perpendicular bisectors? The circumcenter, right? And what's the circumcenter's relationship to the triangle? Equidistant to all the vertices. So if you bisect the sides, that point is equidistant to the vertices. Okay? And that point would be the center of the circumscribed triangle. Now, if I go over here and look at the incenter, what creates the incenter? The angle bisectors. Okay, and so if you do the angle bisectors, they intersect the incenter, and they're equidistant from what? The sides. You see how that relationship kind of works? Bisect this perpendicularly bisect the side, it's equidistant. If you bisect the angle, it's equidistant to the sides. They have that relationship. Okay? And what's the kind of triangle called that's inside the circle that only touches it at 3 points? Inscribed circle, right? And if it's around the triangle, it's circumscribed. All right.